Okay, here we go. So we are getting underway with our final review. There's going to be 6 different topics that we cover. The first one here being measurement and geometry, and the next video is going to be about trigonometry. Um, so at the beginning of this handout in the slides here, there is some conversions, some of them being within the imperial system. So between feet and inches, 12 inches per foot, 3 feet per yard, that kind of thing. And also being able to convert between the two systems, imperial and metric. Um, so 1 inch is equal to 2.54 centimeters, or 1 foot is equal to 0.3048 meters. On the other side of the page here, there's a really similar chart, but it's been flipped. It's all the same kind of conversions. But in the one on the left, the imperial units are the ones that have a 1 in front of them. So 1 inch, 1 foot, 1 yard, and 1 mile. And in the chart on the right, the metric units are the ones that have a 1 in front of them. 1 millimeter, 1 centimeter, 1 meter, and 1 kilometer. So you can use either chart. They will give you the same converted measurement. So use whatever you feel like in a given question, and it's probably going to be fine. So I'm going to jump in and get going. A van is 17 feet long. What is the length in meters? So going between feet and meters, there's a couple of places that we can pull that information from. 1 foot is 0.3048 meters, or 3 feet is 0.9144 meters, or on the other side, I don't think we've got feet over on that one. We have to pick one of these blue arrows. I'm going to pick the second one this time just to try something a little bit maybe unusual. So 17 feet is what's given. And I'm going to multiply by a conversion factor, or like a multiplier, which is a fraction or a ratio of the two equivalent quantities. So a quantity in feet and a quantity in meters. I'm trying to get rid of these feet, so I want feet to go in the denominator. And that means I'm going to have meters show up in the top of my fraction. And in this case, 0.9144 meters is equal to 3 feet. When we do that, we're multiplying a fraction by another number. So it's like we're multiplying by something over 1, if you like seeing the two fractions side by side. We're allowed to reduce any common factors, and in this case, the word feet is a common factor. The units are common. So with the calculator, I'm going to multiply 17 times 0.9144 and then divide by 3. And I'm going to find that that's equal to approximately equal to 5.18 meters. So that's going from an imperial unit to a metric unit. The next question. So the picture in a book measures 35 millimeters by 42 millimeters. What is the area in centimeters squared? So we're going to be doing an area calculation for this, I assume, rectangular piece of paper in a book. The units are given in millimeters, and the question asks our answer to be in centimeters squared. So we need to convert the units. This is one of the easier ones going within the metric system. Millimeters to centimeters. The conversion is just multiplying or dividing by 10, depending which direction you're doing your metric conversion. So 35 millimeters. I'm going to multiply by 1 centimeter per 10 millimeters. And this is a clue to me that I'm going to be dividing by 10. So 35 divided by 10 to find the answer in centimeters. If you know that one, you don't have to show the conversion factor. That's a really common conversion that you've done for years and years now, so I don't expect to see a step for that kind of question. So we can also convert the other dimension of the book, 42 millimeters. That's 4.2 centimeters. All right, so now we've got the two lengths in centimeters. We can do the area calculation. Area of a rectangle is length times width. 3.5 centimeters times 4.2 centimeters. And that comes out to 14.7, so approximately 14.7 centimeters squared. All right, our next question is a three-dimensional one. So this one says a farmer has 1,000 meters squared of shrink wrap left for wrapping hay bales. Will this be enough to cover 100 cylindrical hay bales that are 5 feet long and 5 feet in diameter? Okay, so we have a number that we're going to compare to at the end, but we're just going to worry about these cylindrical hay bales first. If we're trying to cover them, that word is a clue. Covering is like the surface area. We're covering the surface of the hay bale. So we're going to need to picture a cylinder. You can have it on its side like a hay bale, or you can have it upright, it doesn't matter. But the cylinder, it says, is 5 feet long, and the diameter is also 5 feet. All right, so a diameter is not really the dimension that we need to do a cylinder problem. We need a radius, and the radius will just be half of that, so 2.5 feet. And this one, I've drawn the hay bale on its side, but if you imagine tipping it up so the circle's on the ground, this would usually be called its height. And this said diameter was 5 feet. All right, so I'm just jotting down the stuff that we know so far, and then think about what can happen next. If we're trying to figure out the surface area, we're going to need a surface area formula. And for a cylinder, usually that's two circles, 2 pi r squared, and 2 pi r, which is the circumference around the circle, multiplied by the height. So usually that's the formula to use. This question's a little bit tricky because it tells us that one end of the hay bale is left open to allow the hay to breathe. So if there's any farmers or people who are familiar with hay, you don't want the hay to be wet and like rot or grow mold or anything like that. So it's left open to breathe. So instead of having two circles, we're going to get rid of one of those circles. So a slightly adjusted surface area formula. So if we know the radius, the height, if we have those two pieces of information, we should be good to go to find the surface area. I'm just going to double check that the units are in a good form for us. These are both in feet, which is nice. They're the same as each other, but we're going to be comparing to this 1,000 meters squared of shrink wrap, which is a little bit annoying because we have measurements in feet and that's a measurement in meters or meters squared. So we need to convert one of them, and it's usually easier to convert the length dimensions since there's no exponents to worry about. So I'm going to convert these feet into meters. I'm going to pop back to the conversion chart from feet to meters. And this time I'm going to use the first blue arrow. 1 foot is 0.3048 meters. We'll get the same answer no matter which of the foot to meter conversions we pick. So this time I'm going to try the other one. 0.3048 meters. Per 1 foot. So I can see we're just really going to be multiplying by 0.3048, and the units will simplify themselves out. Feet over feet, those are going to disappear, and we'll have a new answer in meters, and it's approximately 0.762. So So we'll do the same with the other dimension. Multiply it by 0.3048 meters per 1 foot. Again, the units are going to simplify themselves out. Feet divided by feet are just going to disappear. And let's see, I could have probably just doubled the other answer, but I'll do it this way anyway. 5 times 0.3048. And that's 1.524. Okay, so I've got a radius in meters, a height in meters. Oh, meters. I can plug those in where the R and the H are in my formula, and then we should be ready to do some calculating. So pi times the radius squared plus 2 pi times the radius times the height. That first term, 0.762 squared, I'm doing the exponent first, then multiply by pi. I get 1.824 for that first term. And we're going to multiply these next four things together. 2 times pi times 0.762 times 1.524. And I see 7.297. Oh, I think I'm being... I just caught myself. I was thinking about 5 for the height, but I did have to convert it to meters. Okay, so we've got two terms. We're going to add them together. And this says 9.12. My units here are meters squared. We converted from feet to meters. So this is one cylinder. One cylinder that I just found the surface area of. The question asks if we're going to have enough to cover 100 cylinders. So we can just scale this up. We can say 100 bales will equal 100 times 9.12, which is 912 meters squared. This is less than the 1,000 meters squared that it says the farmer has. I need a tiny bit more space there. Therefore, yes, he will have enough, or they will have enough. It could be a female farmer. They will have enough to cover 100 bales of hay. Okay, so this one was asked like in the form of a word problem. So I'm making sure to give a word answer at the end. All right, 3 down, 3 to go. The next questions are all three-dimensional as well. We really didn't focus on two-dimensional stuff except for a couple of composite figures. So 3D is our a little bit more fun, a little bit more interesting, a little bit more real life. And that's our focus here. So this one says calculate the surface area of the following. So this has a rectangular base. It looks like a house. A rectangular prism for the base and a triangular prism for the roof. And it's got so many different pieces of information labeled on it. We should have enough given information that this is a pretty straightforward task. So to find the surface area, it doesn't tell me if I need the bottom to be included or not, so I'm going to choose to include it just to be thorough. So I'm going to add a little floor. Let's see if I can make that work. Not bad. So we're going to include the floor as well. So there are pairs of sides or faces of this figure that are the same. There is like the front, or at least to us the front, and a matching side on the back. There is a right and a matching side on the left. There is a roof and a matching side behind it. And there is, let's see, a front of the roof and a matching one behind it. The only one that doesn't have a partner is the floor. Maybe it's silly to include the floor, but I'm going to do it anyway. Because who says this is a house? Maybe it's just a toy that I'm holding. Okay, so find the surface area. I'm going to maybe number these. I'm going to say blue is going to be area of shape number 1, or the area of the blue side. That's a rectangle, so I'll be using length times width. The length is 9. The width in this case is actually its height. It looks like the whole house is 11 centimeters tall, and the roof is 4 centimeters tall. So this is going to be 11 take away 4, or 7 centimeters. And 9 times 7 is 63. We're finding areas here, so it's two-dimensional. We've multiplied 2 dimensions together, so my units are going to be squared. For the second shape, let's look at the green, like the right side of this house. So shape number 2 has an area, it's a rectangle, so again, length times width. The length is 6. The width is the height of that, which we just found out is 7. And 6 times 7 is 42. Next up, I'm going to look at the rectangle that's like the top of the roof, or the side of the roof. It's a rectangle, so I'm using length times width again. This is 9 centimeters across. And I need to figure out this length, which is the same as this one. And it seems like this house is symmetric, left, like the front and the back. So I'm going to assume that if the back here is 5, so is the front. There's nothing there telling me otherwise, so I'm going to assume they're the same length. So 9 times 5 is 45 centimeters squared. Let's see, next up is going to be yellow. I know it doesn't show up as well on the screen, so sorry about that. It's following my color coding. So that one's the triangle. It's the first one of those on this problem. So the formula is going to be base times height divided by 2. The base is like the bottom, the horizontal part of that triangle. It's 6 units across. The height of the roof was 4. And we're going to divide by 2. 6 times 4 is 24. Divided by 2, that's 12. And finally, the floor. I'm going to switch to black for that. That'll be shape number 5. It's a rectangle, so length times width, and it's 9 by 6 centimeters. Multiplying those, I get 54 centimeters squared. Okay, so far I've got a blue, a green, a red, a yellow, and a black. But some of those I'm going to have to double up because there's 2 of them. There's one on the right and the left, or the front and the back. So I'm going to take all of that stuff, all that like pre-planning, and I'm going to actually find the surface area now. So not just looking like one shape at a time, I want to put it all together. So for blue, there's actually 2 of those rectangles. So I can say 2 times area number 1. And for green, there's 2 of those rectangles, one on the right, one on the left. So 2 times area number 2. Add to that, in red, we've got the rectangle for the roof, and there's 2 of those. So 2 times area 3. In yellow, we've got the triangles, and there's 2 of those. So 2 times area 4. And finally, this floor, which is maybe weird to include, but I did it anyway. And there's 1 area like the floor. All right, so 2 times 63 and 2 times 42 and 2 times 45 and 2 times 12, and then the floor, there's only one of those. So I did all the multiplying stuff first to get 126, 84, and 90, and 24, and 54. And then finally you can add those all together to find the total surface area, which is 378. And the units here, this is all in centimeters, so centimeters squared. So that was a lot of work. There's many shapes. Rectangles and triangles should be familiar though. And you've got your formula sheet for the length times width and the base times height over 2. On an evaluation, I would try to make clear whether or not you were supposed to include the floor in your calculation. All right, the final 2 questions for this bit of measurement review. These ones have to do with optimal dimensions for 3-dimensional shapes. Optimal dimensions. Dimensions means we actually want to know the length, the width, the height, the radius, depending on what the shape is. We want those numbers, not just the full volume, which is given. So this first one says we're looking at a cylinder and we know its volume. What are the optimal dimensions? So a diagram is usually helpful, even if you have crummy art skills like I do. So the volume is 4,000. And usually the things that we need to know are radius and height to identify a cylinder. We're not given either of those things, but those are the 2 dimensions that we're going to be finding in this problem. As soon as I read this word optimal, I'm remembering that there is like a best shape. There's a best rectangular prism. There's a best cylinder that uses the least material to cover the surface for a given volume, or it has the biggest volume with a limited amount of surface area. So there's special relationships between the radius and the height for this one that we talked about back in, I think it was week 2. And the trick for this one was that the height had to be equal to twice the radius. That was the best arrangement of like numbers to give us the maximum volume and the minimum surface area, so the least packaging to cover it. So the height is equal to twice the radius, or equal to its diameter, you can think of that as. All right, so that's kind of a fact we talked about back in week 2. With your formula sheet only gives the like general version of the formulas, not the optimal ones. So if you're relying on your formula sheet, you would look up cylinder and volume, and you'd find pi r squared times height. Using this like rectangle, the red rectangle, it says height equals 2 times radius. That means I can change the height to be double the radius if we're talking optimal configurations. So we did all this like legwork back in cycle 2, coming up with the optimization formula for this shape. And it's 2 times pi, just pulling those to the front, and then r squared times another r is r cubed. So back in week 2, we created that optimization formula, and that's an okay place to start if you have printed out a formula sheet, or if you happen to have an old one from like a previous math course, you can add that optimal formula onto it. So now we're given a volume of 4,000. So the volume is 4,000. And 2 pi r cubed is the right-hand side of that formula. So all I did was replace the volume with the number given in the question. To find the optimal dimensions, that means we're going to be solving for, it looks like radius in this case. So we need to get rid of 2 pi using division. That comes out to 636.62 equals radius cubed. And I don't want radius cubed, I just want plain old radius. So we're going to get rid of the cube using a cubed root. And we'll do the same to the other side. And that will leave us with just the r on the right side. And with my calculator, I've got a cubed root button that has a little 3 sitting in the front of it. And when I do cubed root of 636.62, the answer I see is 8.6. And this was in centimeters. So this is like nearly done, but there's 2 different dimensions that we need to know, the radius and the height. So my last little piece of this, I know I'm kind of out of space here, but now that I know the radius, I can plunk it back into my height equals 2r formula. And we'll just find 2 times 8.6, which is 17.2 centimeters. Okay, so this section here in the middle, you might not need to write that out ever again if you jot the highlighted formula down as an optimal cylinder formula. And we would just be doing the blue stuff and the green stuff if we were looking at a new question. Okay, so the last one is a rectangular box. So I'm picturing, it can be long. Oh my goodness, this is my worst ever. There we go, I'll make it a tall box. Much better. Art is not my forte here. So this one has a surface area of 300 millimeters cubed. So this is measuring in millimeters. And again, we want the optimal dimensions. There is a best rectangular prism. The optimal one is actually a cube. With all sides the same. Whereas this one, which is like tall and skinny, length times width times height, and these ones don't have equal dimensions necessarily. So here's the rectangular box. Here is the very special case of the cube, which is optimal. And for this one, the surface area formula is nice. I like using SA for surface area. On your formula sheet, it just says A, so pick whatever you like. But there is a square at the front whose area is S squared, and there's 6 of those that are identical. So 6 S squareds. The question tells us that the surface area is 300, so that's given. I'm trying to find some dimensions, so I want to know how long is this S side. So we're going to get rid of the 6. 300 over 6 is 50. 50 is equal to S squared. I want to get rid of that square, so I'm going to square root it and do the same to the other side. And the square root of 50 is approximately 7.1. Therefore, the dimensions are 7.1 millimeters by 7.1 millimeters by 7.1 millimeters. It's a cube. All right, so that's it for measurement. There's some stuff in this recap that was about 3-dimensional shapes, about optimizing 3-dimensional shapes and using these kind of adjusted formulas for like a special case. We also looked at the metric conversions, metric to imperial, multiplying by some kind of conversion factor that uses the right 2 units, the ones you have and the ones you want. So that's it for measurement and geometry. I'll stop the video there.